Hello everyone, in this video we are going to discuss how you can get the numerical solution of an ordinary differential equation in Python. We have an example of a radioactive decay equation. We know the radioactive decay equation relates the amount by which a particular radioactive element has decayed. So it relates between how much has been there in the beginning and how much is existing after a particular elapse of time. So we have a differential equation of dy dt equal to negative ky, whereby y is of course now the function that is a function of time. So we are going to look at NumPy, then we also utilize the library of SciPy and Matplotlib to help us to plot. So import NumPy as NP, then from SciPy.integrate import oddEint. So oddEint helps us to solve a differential equation numerically. In other words, it gives us numerical values of the differential equation, and then you can plot it and see how the function is behaving after a particular time t or after a particular interval of the independent variable that could have been chosen. Then importing matplotlib.pyplot as plot helps us during plotting of these results produced by the oddEint. Now we need to define this equation. We have this method and we have several methods of defining that differential equation. So here we are going to use the defining the function, and is going to be a model which is taking t and k as independent variables, and y is a dependent variables on t and k. Then of course dy dt is equal to negative k. In case you don't have this, then automatically the indent will be at the end. So if you put this colon, then the indent will bring you directly below the def, meaning whatever we are now defining is within what between defining and what is going to be returned. So if we define the function which is y and is a function of t, then with k also involved, then dy dt is equal to negative k times y. As we have said, for radioactivity, in most cases, this is the differential equation that defines the radioactive decaying process. So return dy dt because it's what we are interested in. We know dy dt is the one which is equal to that negative ky, but we have already taken the model or the function taking taking y as majorly a dependent variable on t and k. So we have to also note we need to give it initial conditions. So at y naught, in other words, at t is equal to 0, there is a particular value of y. So since it is a first order differential equation, then it is going to have only one initial condition. If it was a second order differential equation, then it would have two initial conditions, one which would be y of t at t is equal to 0, then also dy dt at t is equal to 0. Then we need to define the values of t. So we can say they are going to range from 0 maybe to 20. Then we also want to take 3 arguments where we see the effect of k. In other words, this is a constant, but we want to see the different responses from the different k values. So when k is equal to 0.1, then y1, the output is going to be odd int. This odd int is helping us to integrate this differential equation, and with respect of course to t, but with a particular initial condition. So it is going to integrate that, then at looking at the initial conditions of y naught, which is the value of y at t is equal to 0, then the t value also, then taking now we are using this args is taking the argument of k. In other words, this is taking it as a tuple. So we are using a tuple, but which is helping us to take k as the argument in that particular value of y1. Then we go to y2, where we can also define k. Maybe we make it 0.3. Then we also say odd int y naught t argument of k. We have already defined k here. Actually, we can even say k1. Then here we say k1. Then this one we call it k2 for us to be clearer. K2. Then we go to k3, which is 0.5, and here we will also say k3. Okay. Now when we go to plot, we will also now plot y1 against t values. So we go to plot y1. If we want to plot y1, we want maybe the color of the plot. We can take it to be, it can be green. Okay, a green solid line. Then the line width can be, we can say maybe let it be 3. Then we say the label of that line is going to be, when we create a legend, it is going to be k1 equal to 0.1. Then we go to plot number 2, which is plot t. Then y2, we want it to be, maybe if it is maybe let us make it black with a dash dot. We will see it will be a dash with a dot at the end, like that, like that, like that. Then let the line width be maybe also 3. Then we move. The k is going to be, k is equal to 0.3. Is 0.3, and it is k2. Then y3 is also going to be plotted on t values, and maybe let us use blue, a solid line of blue. Then we are going to, actually it will be a dashed line. Then we will have a line width of, maybe we can maintain that 2. Then let this become k3. Then let us plot x label. We are labeling now the axis. We can say that axis is time. Of course, time is on the x-axis. Then the font size can be, we can leave it at 25. Then we can also actually say, because we could want it bold, so we can say font weight is equal to bold. Okay, we also go to y and say font weight is equal to board. Then we cross. That is the label for y-axis. Then we have to plot argument. We have to plot the legend, because the legend is going to come due to the fact that we have put labels. The label function is equal to that, so it will come on our plot. But if we don't give it the legend, then it is this legend that calls it to be labeled as legend on our plot. Then the title, we want it to be numerical solution of our differential equation, and the font size is 30 with the font weight as bold, and we can actually say maybe grid. We say PLT. We can also wish to have the grid. So let's run. Okay, you can see now our plot is very smart, with the title bold, numerical solution, y of t bold, and t, time on the x-axis, is bold. Then this is now our K1. K1 is green. Then K3 is bold, also a solid line. And the dash dot, which is our K, the argument of K2, which is also equal to 0.3. So you can see how the K value or the constant affects the output or the trend of the graph of the decaying curve. In other words, you can see when you have a smaller K, when you have when you have a bigger K value, when you have a smaller and the smallest, you can see the effects. And therefore, this is how you are able to show this in this particular Python as you code it. And therefore, that is the output that you would come out with. Thank you so much.